Hello there. In this video, I'm going to go through MCQs in medical physiology under the topic muscle tissue physiology. So the first question reads, which of the following best describes the changes in cell volume that will occur when red blood cells previously equilibrated in a 280 milli or smaller solution of sodium chloride are placed in a solution of 140 millimolar sodium chloride containing 20 millimolar urea, a relatively large but permeable molecule. So A, cells shrink initially, then swell over time and release. And B, cells shrink transiently and return to their original volume over time. And C, cells swell and release. D, cells swell transiently and return to their original volume over time. And E, no changes in cell volume will occur. So what will happen to this cell, which is a red blood cell, and which was previously in 208 milli or smaller solution of sodium chloride, when it is placed in 140 millimolar of sodium. So 140 millimolar of sodium is the same as 280 in milliosmoles, because 1 millimolar is equivalent to 1 milliosmoles per liter if the compound do not dissociate. But for sodium chloride, if we have 1 millimolar, then it is equals to 2 milliosmoles per liter. So why? Because it dissociates. So here we have 140 millimolar of sodium chloride, so it will dissociate and form 2 active osmoses, meaning 140 will give us 280. So here we have the same solution, concentration of sodium chloride, because we had 280, and in this other solution where this red blood cell is being placed is also 280. But there is another additional 20 millimolar of urea. Okay, so what will happen to this cell? So this cell, we have a beaker where we have put that 280 milliosmoles of sodium, and we are placing a cell in it. But initially that cell was also in 280 milliosmolar, which is 280. But here we have another additional of 20, meaning this one is more concentrated than that one. But now the question here is saying, what will happen to the cell? What will happen to the cell is that the cell will shrink. Why? Because it is being put in a concentrated 20 milliosmoles of urea. So meaning there is an additional on top of 280. There is an addition of 20. Okay, so it will shrink transiently and return to original volume over time. It returns to original over time. Why? Because this urea, it is relatively large but permeable molecule. It can cross the cell membrane of the cell. So over time the cell will return to its original volume. So the correct answer for question 1 is B. So let's move on to question 2. Question 2 reads, what is the calculated osmolarity of a solution containing 12 millimolar sodium chloride, 4 millimolar potassium chloride, and 2 millimolar calcium chloride in milliosmolar per liter. Milliosmoles per liter. So A, we have 16, B 26, C 29, 32, G, E 38, and F 42. So to calculate the osmolarity, we look at the number of millimolar and the compound which is involved. So in this case, we have 12 millimolar of sodium chloride. So in milliosmoles, sodium chloride will dissociate. Then when it dissociates, it forms 2, meaning we are going to multiply 12 by 2 and we have 24. So these are the active osmoles for sodium chloride. And then for potassium, it has 4, but here it is potassium chloride, so it will also dissociate. So 4 will be equals to 8 milliosmoles. And then from there, we have the calcium chloride. Calcium chloride here, it is 2 millimolar, but when it dissociates, it forms a 3, because we have 1 calcium ion and 2 chloride ions. So 2 by 3, it will be 6. So to find the total milliosmoles per liter, then we are going to add all these milliosmoles. So we have 24 plus 8 plus 6, which is equals to 38. So the correct answer for question 2 is E, 38. We move on to question 3. So for question 3, we are going to use this table here to answer the following 4 questions, which is question 3, 4, 5, and 6. So question 3 reads, what is the equilibrium potential for chloride across the plasma membrane of this cell, the cell which has these concentrations of these ions? So what is the equilibrium potential for chloride? So to find the equilibrium potential, we are going to use the next equation. So we are going to put into consideration the extracellular millimolar and intracellular millimolar. So the next equation says the equilibrium potential for chlorine is equals to 61, which is a calculated gas constant with the temperature, and over Z, which is the charge, the valence for chlorine, multiplied by log concentration of chlorine outside the cell over concentration of chlorine inside the cell. So here we simply replace 61 over the valence of chlorine is -1, multiplied by the log concentration of chlorine inside the cell, outside the cell is 110 here, over concentration of chlorine inside the cell, which is 11. So here we're going to have -61, because 61 over -1 there to be -61, and then log 110 over 11 to be 1. So the equilibrium potential for chlorine will be -61 millivolts. That's how to get it. So the correct answer will be E. So question 4, correct answer is E. Okay, so we move on to question 5. Question 5 reads, if the membrane potential of this cell is -80 millivolts, so the driving force is greatest for which ion? So the driving force is greatest for which ion if the membrane potential is -80 millivolts. So to find the driving force, what we do, driving force is equals to membrane potential minus equilibrium potential for each and every ion which is there. So membrane potential, we have it is negative 80 millivolts. Now the equilibrium potential we calculate using the NST equation. So we are going to say negative 80 minus the equilibrium potential for each and every ion of these. So the one which has the greatest equilibrium potential here, the greatest driving force will be calcium, because if we calculate the equilibrium potential for calcium, we are going to get positive 131. So positive 131 minus the potential minus the membrane potential, we are going to have a big positive number. So the correct answer will be A. It is calcium in this case which has the greatest driving force. So question 6. Question 6 reads, if this cell were permeable only to potassium, what would be the effect of reducing the extracellular potassium concentration from 14 to 1.4 millimolar? So what would be the effect of reducing the concentration of potassium from this 14 extracellular to 1.4? So to find the effect, we need to calculate the equilibrium potential. We know that for 14, the equilibrium potential was negative 61 millivolts. Now what will happen if we reduce the extracellular concentration? So to do that, we are going to use the NST equation, where we simply divide the concentration of potassium outside over 140, we get the log of that, and then from there we multiply by 61 and we are going to get negative 122 millivolts. So we have seen that it has moved from negative 61 and it is now negative 122, meaning the answer is D. It is 122 millivolts hyperpolarized. Why? Because it has been further, become negative, more negative. So it has been hyperpolarized. Move on to question 7. So question 7 reads, why is the tension development maximal between points B and C in this diagram here? So this diagram is showing the tension development in a muscle tissue against the length of the sarcomere. So they're asking, why is the tension development maximal between points B and C? Why is it maximal? So A, actin filaments are overlapping each other. B, myosin filaments are overlapping each other. C, the myosin filament is at its minimal length. D, the Z disc of the sarcomere about the end of the myosin filament. And E, there is optimal overlap between the actin and myosin filament. And F, there is minimal overlap between the actin and myosin filament. So when you look at this question, at B and C, we can see that the length of the sarcomere is increasing this side, but the tension is not increasing. So that is, the tension is not increasing. So we can say there is optimal overlapping between the actin and the myosin filament. It is at optimum. Actin and myosin are overlapping optimum at optimum duration. That is the correct answer for question 7. Question 8. Simple diffusion and facilitated diffusion share which of the following characteristic? So they share which characteristic? A, can be blocked by specific inhibitors? No. B, do not require adenosine triphosphate? Yeah. So correct answer is B. They do not require adenosine triphosphate. Simple diffusion and facilitated, they do not require ATP. The correct answer is B. Require transport protein? No. Saturation kinetics? No. Transport solute against concentration gradient? No. So the correct answer is B. Question 9. Excitation contraction coupling in skeletal muscle involves all the following except 1. Which one is this exception? A, ATP hydrolysis. B, binding of calcium to calmodulin. C, conformation change in dihydropyridine receptor. D, depolarization of the transverse tubule membrane. E, increase the sodium conductance of sarcolemma. So the correct answer for 9, the exception is binding of calcium to calmodulin. Calcium, when it is released, it binds to troponin C, not on calmodulin. So this is incorrect. So the correct answer is the exception is B. Question 10. A single contraction of skeletal muscle is most likely to be terminated by which of the following action? A, closure of the postsynaptic nicotic acetylcholine receptor. B, removal of acetylcholine from the neuromuscular junction. C, removal of calcium from the terminal of the motor neuron. D, removal of sarcoplasmic calcium. E, return of the dihydropyridine receptor to its resting conformation. So 10, to stop, to terminate a single contraction, what you can do, you remove the sarcoplasmic calcium. If you close the postsynaptic nicotic acetylcholine receptor minus removing the sarcoplasmic calcium, the calcium inside the muscle cell, the contraction will continue. If you remove calcium from the terminal of the motor neuron minus removing the calcium in the sarcoplasmic reticulum, in the sarcoplasmic of the muscle tissue, the contraction will still occur. So the best way, you simply remove the sarcoplasmic calcium inside the muscle tissue, then the single contraction will be terminated, because what causes contraction is calcium, which binds on the troponin C, and then troponin C causes a conformation change in the troponin myosin complex, which exposes active sites where myosin binds and contraction occurs. So removing sarcoplasmic calcium causes muscle contraction, causes the muscle to relax. If you remove calcium, then the muscle relax. So correct answer for question 10 is D. So thank you very much for watching. Don't forget to like, subscribe, and hit the notification bell so that you don't miss any of my videos, and leave your comment concerning this video in the comment section below.